Remember first time I opened up this book and saw the picture of the old radio there on figure 2-1. Reminded me of like clocks like this. You know, sometimes it's difficult when young people come up to the office and they want to know what time it is, and we refer to a clock like this, and they look at it and they go, "But what time is it?" Do you all have difficulty reading clocks with hands on it? I'll sometimes say, "Well, the small hand is just before the 9, and the big hand is just after the 6. About what time is it?" I don't know, because they're used to the digital readouts and stuff like that. This old radio here, it's going to be as foreign as one day when people say, "Hey, look I found these old DVDs." DVDs? What's a DVD? Or computers, when you go buy them now, they don't even have DVDs, drives on them, because everything is MP3 downloads and things like that. Go straight, you got to buy an external hard drive or external drive to do a lot of that. This picture of the old radio, the analogy they're making here is, if you've ever had an old piece of electronic gear, like a radio, and you've had that pleasure of maybe taking a soldering iron and some wire snippers and going in and taking it apart and seeing all the pieces that are in it and separating everything, maybe putting all the resistors on one side, all the capacitors on the other side. Has anybody ever done that? Oh, that's a lot of fun, man. Taking old gear apart. But just because you can open it up and take it apart and maybe see all the pieces that are inside and maybe separate all the pieces that are inside, does that mean when you're done that you understand how a radio works? Not really. You can see, maybe conceptualize some of the processes, you know. And later on, when you start drawing electrical circuits using, you know, like I said, capacitors, resistors, maybe even in the future using Boolean logic to form logic circuits or things like that, you can conceptualize these things, but taking it and actually producing a piece of equipment that does what you say it's supposed to do is a different matter. And to create the thing from scratch, well, I'll remind you that as creatures, we never create out of nothing like God does. All we ever do is rearrange things. God makes out of nothing, we make out of something, which makes our creations something different than what he does. And what we're talking about today is basically matter. What is something? What is anything? What is it made out of? And how have scientific historians or people that are in the philosophy of science, how have they understood what it means to be something as opposed to being nothing? And we're not going to get into philosophy of, are you something? Ray, are you something? And how do you know you're something? Or do you just think you're something? You don't know. Okay, I made a statement on a paper I was working on yesterday that ultimately all issues, and I've said this before, ultimately all discussions come back to philosophy. That's why they call, you know, the highest degree you can get is a PhD, a doctor of philosophy, because it's your philosophy on things and how you understand things that will drive how you come to conclusions about certain things. And as scientists, we have to be cognizant, we've got to be aware that whenever we are investigating something or making decisions about something or considering something, that we are very, very prone to our own biases. We're very, very prone to find what we already believe to be there. A lot of times in science, multiple scientists looking at the same evidence can come to radically different conclusions, and under investigation, oftentimes that is because they carry their own biases into the investigation, or more specifically, into the interpretation of the data, the interpretation of the results. That's why you can have an evolutionary biologist and a creationist side by side looking at the same information. Or maybe the easiest for us to visualize is a evolutionary geologist and a creationist geologist looking at the same geological record and come to radically different conclusions about what it says. And both be able to look at that and say, but I've got evidence. Here's my evidence. And often point to the same evidence and come up with radically different conclusions. So how you think about things drastically impacts how you understand things. And sometimes there have been understandings in the past that worked for a while, but really didn't hold sway for long. The world around them has changed. Oftentimes also, when somebody that has some level of authority, when people speak that are respected by the population, sometimes what they say is accepted as being true without there being any real critical investigation of it. There's a popular figure that comes out and says, you know what? The world is flat. And guess what? Generations believe the world is flat. Why? Because this person said so. And nobody dares speak against that person. He's so well loved. He's so appreciated. He must be right. Therefore, what he says is true, which is fine if that person's correct. But if that person's wrong, we have generations of error. So today we're going to start talking about the idea of matter and what is something, and how somethingness, sometimes I call stuffness, has been thought of in history. And first of all, starting with one of those figures that people tended not to speak against, someone by the name of Plato. You may have heard of him. Okay, Plato had some very strong opinions about a lot of different things. And when Plato spoke, it was like you're too young to know this, but there used to be a commercial called for E.F. Hutton, and there was a comment at the end of the commercial where it would say, when E.F. Hutton speaks, people listen. You know, there'd be different scenes like in a restaurant, and these two folks would be talking about investments, and there's all this noise going on, and one person would say what they thought, and say, well, what does your broker say? Well, my broker's E.F. Hutton, and E.F. Hutton says, and suddenly all motion, all noise stopped, and as the camera pulled back, everybody was leaning in to hear what E.F. Hutton was about to say. You know, what the broker kind of saying, well, this is the authority, and when this person speaks, you better listen. That was the attitude of many people, of virtually everybody, when significant characters like Plato spoke. And Plato said things about a lot of things. And one of the things he spoke about was matter. And here's the theory, the continuous theory of matter. The idea for the continuous theory of matter is that matter is just a solid block of stuff. And let's say we're not going to get concerned with what the stuff is. You can imagine whatever you want, whether it's Laffy Taffy or whatever, right? Here's a block of something. The idea was, if I have a block of something, I can take it and then cut it in half, and what do I have? I've got 2 blocks of exactly the same thing. If I take that and I cut it in half again, you know, now I have 4 blocks of exactly the same thing, and then start chopping it into thinner and thinner and thinner and thinner pieces, smaller and smaller and smaller pieces, to doing that an infinite number of times. So doing that to infinity. I know it's starting to sound like calculus, but it's not. We're going to chop it into pieces all the way to the end, get it smaller and smaller and smaller and smaller, and every time you cut it smaller, what you have is a smaller piece that looks exactly like the bigger piece. I mean, it's almost like, if you want to imagine this, those old Play-Doh fun factories that you had, the matter is like Play-Doh, and you put it in and you push it out, and when it comes out, it's in different shapes. And that matter was continuous. It's all blue Play-Doh, let's say. Maybe some of you will come in here with my Play-Doh and my Lego blocks, because we can do a lot of chemistry with Play-Doh and Legos. But squeeze that stuff out, okay, and it comes through a little star. You get this tube, or this long string of Play-Doh shaped like a star, right? Well, that would be one type of matter. And we put the same Play-Doh in, and we squeeze it through the oval, and we get an oval rope of Play-Doh. And we put it through the square, and we get a square rope of Play-Doh. And the idea was that matter was continuous. You could keep chopping in smaller and smaller pieces infinitely, and it would always be the same stuff, just less of it. And that what made things look different was the shape it was in. So because certain matter looked like an oval, and certain matter looked like a rectangle, it's like a rectangle versus a square versus some star shape, and I'm making this up, but the idea was that matter looked different because it was basically ropes of the same stuff, just in different shapes. And that's what made this book look different than this podium, than this floor, the whiteboard, the marker, because the stuff that they were made of were different shapes, but it's just all Play-Doh. It's all matter. It's just paste. That was the thinking of Plato and the ancient Greek philosophers until about 400 years before Christ. And about 400 years before Christ, the philosopher by the name of Democritus, they talk about him starting on page 45 in your text. Democritus came up with this idea that maybe matter isn't just a solid chunk of stuff, and objects weren't just solid pieces of stuff, but rather a bunch of small pieces all stuck together that look like they're one solid thing. And the example they give in here, which you'll hear all the time, this is always used, how Democritus came up with this, is he was walking along and he looked in the distance and he saw a beach line. And as he was sitting there observing the beach, it struck him. He must have obviously been thinking about Plato and matter. You know, people, geeks, we think about stuff like that sometimes. And so he's walking along, he sees the beach, and he's saying, wow, look at that beach. That beach is made out of, the beach is made out of stuff that's beach. It's beach stuff. It's stuff in the shape that makes it look like beach. But wait a minute, I know when I get there and I walk through the beach, I'm going to have pieces of beach stuck to my feet. It's not really solid. It's actually a whole bunch of little pieces of things we call sand, right? It's a whole bunch of little pieces of sand. From a distance, it looks like one chunk of beach. You know, the farther away from something, the more it looks like a painting, you know. You can just take one color, maybe go, there, I painted the beach. But when you get real close to it, I can't do that anymore. There's a bunch of different pieces. There's a bunch of different shades. You can almost see at places where there might be one type of mineral over here that's not over here. And just think about this concept. And he said, I can't simply say that this beach is made out of beach stuff. This beach is actually made out of a bunch of little pieces that have their own, kind of like their own identity, right? I pick up the sand and look at it and I go, well, that piece isn't like this piece. That grain over here is very different from this grain over here. When I put it all together and look at it from a distance, yeah, it looks like just beach. But when I look at it closely, I can see lots of uniqueness between the pieces. What if that's true of all things that appear to be made out of consistent stuff, but they only appear that way because we can't see it close enough? I mean, if we were able to look closer and closer and closer, maybe at some level it actually looks like one solid, identical type of stuff, but real close it's actually made up of different kind of stuff. And frankly, that view stood in direct opposition to Plato. So you can imagine, if everybody loves Plato, and you step up and go, I think Plato's wrong, what happens? Who do you think you are? You don't have the authority to stand up to Plato. It's kind of like saying, you know what? To a much lesser degree, be kind of saying, I don't think Mr. Baker really understands that reaction very well. I think I'll confront him in class and see what the class thinks. I mean, there was that kind of a bold move on Democritus' part. The problem was, this was all concept, because at the time they didn't have the kind of instruments we have, or even rudimentary instruments that they had in the early 15, 16, 1700s. This was 1,000 years before then, maybe to almost 2,000 years before then. And so all they had to work with was what they could see, what they could observe. And they didn't have the technology to be able to observe at the level that Democritus would require for us to be able to say, you know what? Democritus was onto something here. Stuff is not just all the same thing in different shapes. Stuff is actually different things, in some cases brought together, and from a distance appear to be just one thing. But that's not the case in reality. So it wasn't until about the 1700s, actually, when this whole idea of the discontinuous theory of matter started to really take shape, take form, and become the prevailing way that we understand matter today. Okay? Now, here's the deal. We're going to talk about decomposition in just a moment. And when we think about decomposition in chemistry, it's very different than decomposition in biology. When you think of decomposition in biology, what do you think of? Has everybody in here had biology? Okay, I haven't. I know what it means. You have. Biology, decomposition. Think of things that are like messy, gooey, you don't want to step in, right? It's like, oh, I forgot to put that in the fridge before we went on the holiday. Ew. It started to decompose. Decomposition in chemistry is not nearly as revolting as decomposition in biology. But what is decomposition? What does it mean to you when you say something has decomposed? Even if you think in terms of biology, even if you think in terms of CSI or whatever show you're thinking about, what does it mean when something decomposes? It rots. Okay, that's another word. But what is happening when something decomposes or rots? What's happening? Maybe you think about it in in contrast. When a composer composes, he's doing the opposite of decomposing. He's composing, okay? Or maybe when you compost, what are you doing? You're actually bringing things together, but then you're letting it decompose, right? When you're composting. To decompose something means to have it break down into its pieces. Have it basically come apart is what it means to decompose. When a body is decomposing, when anything decomposes, and in chemistry we're going to talk about chemicals decomposing. This idea of decomposition ties into, on page 46, we're going to start talking about the law of mass conservation. A gentleman whose name you're going to become familiar with is Antoine Lavoisier, who's considered the inventor of chemistry. Antoine Lavoisier. And this idea of the law of mass conservation, whether you say it's the law of mass conservation, how are you most familiar with saying it? It's not the law of mass conservation, it's the law of conservation of mass. Same thing. And what does it mean? Just think about the name itself. The law of mass conservation. Will? Briscoe. What does it mean to conserve something? Right, you're keeping it, right? You're not letting it get away. The law of mass conservation means we're going to keep something, we're going to save something, and we're saving the mass. And here's the idea, that in a closed system, now, unless you're told otherwise, the assumption is that we're working in a closed system. Two types of systems, closed systems and open systems. A closed system means that I'm keeping track of everything that happens within that space. So maybe in your mind when you say this is taking place in a closed system, I want you to think of maybe like a large fish tank with a top on it, okay? We talk about a closed system, it means, okay, we're going to put everything that we're about to react or decompose or something's about to happen, we're going to put it inside of this fish tank, we're going to seal it, and then we're going to have a way of making the reaction happen. Okay, it's closed, meaning nothing can escape and nothing can be introduced from outside the system. You're kind of walling off that whole experiment. It's a closed system. An open system would be like that same aquarium, but you never put the lid on it. And so, if you have something burning inside of a fish tank and you've got a seal on the top, yeah, it's going to collect all the smoke, all the ash. It's also going to use up all the oxygen, and eventually the flame is going to go out. The flame's going to go out because it runs out of oxygen. And it runs out of oxygen because it's a closed system. No new oxygen can get in from the outside. If you have an open system, you're basically just making a campfire in an aquarium. It's going to burn because as everything comes out of it, it needs more oxygen. Well, new oxygen from the outside goes into it. You're allowing things to come in and out of the system. So generally, when we're talking about systems, we're going to talk about closed systems. And so we talk about the conservation of mass. You need to keep in your mind we're talking about a closed system. Nothing is coming in from the outside, and nothing from the inside is going out. We're trapping everything that's being considered. So the law of mass conservation, on 46, you see it's in blue, which means it's something you're expected to memorize. The law of mass conservation means that matter cannot be created or destroyed. It can only change forms. It can only change forms. And primarily this first part, we're not talking about changing forms between mass and energy. We're not going to be doing that in this course. What we're talking about is changing forms in terms of its matter, in terms of its stuffness. What does it appear to be versus what is it? And it changes what it appears to be because often we can bring about transformations. We can make things and we can decompose things. We can compose and we can decompose. And again, I wished I brought my Duplos or my Legos. We can use those in chemistry. So think about this. When you're making something, when you have something, it's a Lego creation. Okay? All these Legos together to form whatever it is you've made. That's the piece of matter we're investigating. If I were to say, okay, I'm going to take that matter, that Lego creation, and break it down into its pieces, I can pull all the different Legos off of that. And I can say, well, let me bring all the blue Legos together and all the red Legos together and all the yellow Legos together. And maybe in our thinking, we'll say, well, those will come down to be different components that are the same thing. All the yellows are the same thing, and all the blues are the same thing, and all the reds are the same thing. But together, they form something different that's made up of red, blues, and yellows. Okay? You can see that if we think of matter as Legos, and I break it down, that I can get this Democritus idea of discontinuous matter, because it looks like a nice castle or T-Rex or whatever it is you built for your Lego creation. Remember, you used to go, Mom, look, this. I want to glue it together and save it forever, right? No, we're not going to do that. Why? Because tomorrow you want to build something else. And to build that something else, you have to take this all apart, so you have the blocks to build the new thing tomorrow. But as we break it apart, we then say, okay, but I get to a place where I have the Lego, but I can't break it down anymore. I can't, unless, you're one of those kids that gets out the knife or the hammer and like snapping Legos, But we're going to say you can't do that, because in chemistry, when we're snapping Legos, the analogy would be we've just created nuclear fusion, and our game kind of ends because we all blow up. Okay, so we're not going to go to the breaking of the Lego, but we are going to go down to separating the Legos. This idea of conservation mass would say, okay, let's say I have something that I've created out of Legos, and I put it on the triple beam balance, and I take the mass of that thing, whatever it is that I've made. And then I were to go and take all the pieces apart and make stacks of the different colors and put them back on the triple beam balance, would it have more, less, or the same mass as I started with? In other words, I'm not creating more stuff by the way I rearrange it, right? I have the same stuff. Or if I go the other way, if I have a stack of blue, stack of yellow, stack of reds, and I put them on the triple beam balance, I'll get a particular mass. I'll have a certain amount of stuff. If I take those building blocks and I build something out of them, make a creation, and I put that creation back on the triple beam balance, it should have exactly the same mass as the pieces had combined. That's basically what the law of conservation of mass, or law of mass conservation, says. If I have something and it has a particular mass, and then I break it up into all its pieces and I take the mass of all the pieces, the mass of the pieces equals the mass of the original thing. And the reason it's the same is because I haven't brought any new stuff in, and I haven't thrown any of the stuff I have out. I'm operating in a closed system. Okay? So in terms of chemistry, they started talking about this idea of burning wood. If I have a log, and you burn that log, whether it's, we have to pretend here for a minute, because I just said closed systems with flame, there's certain things that run out and the flame stops and all of that, but let's just think conceptually now. If we have a big space, let's say the space is the gym, okay? Big space. So I'm pretty confident if we started a log on fire in the middle, not only would make a mess, hopefully not catch the floor on fire, but we could burn that whole log before we ran out of oxygen in that space. So if we took that log and we started to burn it, and we have the campfire going right there in the middle of the gym, and we're looking at it, what are some of the things that we're going to notice over time that's happening to that log? What are some physical things that are going to happen to that log? Okay, a type of decomposition is taking place, right? It's combusting. Okay, so what do you see happening to it? I mean, like, think in your mind, a log just when it's burning on its own, and then we come back an hour later. What's it going to look like different? How different is it going to look? I mean, it's going to be different than it was when we left it, right? Black or gray. Okay, is it still going to be recognizable for maybe the log it was? Maybe when you put it on there was a little carving in it that said, LJ heart whatever on there, and it burns, and then you come back and go, hey, where'd the little tree tattoo go? Oh, it's ash, right? When you come up and you see the ash there, you want to go say, hey, let's go build a house with this, or let's go build something out of this. No, it's not wood like you would understand wood anymore, right? It's ash. But if you stop and go, wait a minute, and early scientists, because all they had to work with was their own observation, they would say, but look I burned that wood, and guess what? There's not as much stuff as there used to be, so some of the stuff must have disappeared. Some stuff that used to be there no longer exists anymore because I can't see it. Okay? Because you all know, you still operate under the assumption that if you can't see it, it doesn't exist. Right? So let's not get too critical with these early scientists. It's kind of like, how come some people still miss the idea that, hey, this air is in the room, and I'm putting my hand through the air, even though we can't see it, we believe it's here. The reason why we don't believe it's here is because we can't see it. The problem is our pieces are so small in chemistry that they're beyond our ability to see with the naked eye. We need to use instruments to do that. And I will at times say, let's get on Frizzle's bus and let's go. And so hopefully you all understand what I mean by that is the Magic School Bus. And what we're going to be doing is trying to visualize what it's like to go down to the level where things that we cannot see can actually be seen. So, burning a log, it used to be maybe a massive wood pile. Now it's a small pile of ash. Maybe you carried the wood over there and it's like, oh man, all this wood, I feel like I'm in physiology. Okay? And then when you're done, you come over and you sweep it up and you put it into a little plastic bag and you just carry it away. It's light as a feather. And you're going, all this stuff that used to be here has just disappeared. It no longer exists. Actually, it does exist. It still exists, but it exists in a different form than it was before. A lot of what you saw is actually now in the air that you're walking through. It's gone from being solid to being gas. It's gone from being something you had to carry to something you walk through as you carry what remains solid, the ashes, out of the room. A lot of what was in that log was actually, first of all, nothing. Remember we talked about this before. Most of everything that's something is actually nothing. Second, a lot of what was in that log was water. What's happened to all the water that was in that log? When you're carrying a log over there, think of it as a water bottle. What you're going to burn is the bottle. The water inside is not going to burn. Guess what happened to that water? It all evaporated. It's in the air around you. It's now going to condense on the window when the AC's too cold inside. It's still there in the room. It's just in a different place, in a different form. It hasn't disappeared. They mention over on page 49 that this idea of conservation of matter was a theory. Eventually they were able to test it. It was a hypothesis that Lavoisier and folks had, right? It was a theory. It was a hypothesis. After testing, it proved accurate to them. It became a theory, and after extensive theory, it became law. And so that now the idea that there's a law of conservation of matter, people don't start from the position of questioning it. They start from the position of accepting it and have to prove that it's not right as opposed to proving it is right. So law of conservation of momentum. Example 2.1 walks through this, and rather than doing it, we're just going to talk about it real quickly. It says a chemist notices that when given enough energy, a certain white powder changes into two different substances, tin and oxygen. The chemist watches 151 grams of the powder undergo the change, and they collect the tin that was formed, and it measures to be 119 grams. Unfortunately, the oxygen could not be collected, so how much oxygen was made? That's a paraphrase of the question. If I have 151 grams, and I take that 151 grams of this stuff, and I go through a process, and at the end of the process, it produces 119 grams of one thing, and it creates something else, or it doesn't create, but it produces something else. How many grams of that other thing must have been produced? Well, I started with something which was my Lego creation, that's 151 grams, and it's only made up of two different colors, reds and blues. I've got 119 grams of reds, so how many grams of blues do I have? $32 grams. How do I know that it's 32 grams? Because 119 and 32 equal 151. So whatever I start with, if I'm not adding or taking anything away from it, I'm just taking it and changing it and rearranging it, the sum of the products is equal to the mass of the original. The law of conservation of mass. On Your Own 2.1 says, a compound is decomposed into its constituent elements of carbon, nitrogen, and hydrogen. if in the decomposition 12.0 grams of carbon (14 grams of nitrogen) and 3 grams of hydrogen are formed, what was the mass of the compound that was decomposed? So if the mass of all the pieces that make it up are 12 and 14 and 3, so what's the sum of the masses here? 29 grams, right? 12 and 14 is 26 plus 3 is 29. 29 grams altogether, meaning that I don't even have to know what the formula was for what I started with, but I do know that what I started with is 29 grams. 29 grams of something broke down into 12 grams of one thing, 14 grams of another thing, and 3 grams of the third thing. Why? Because the law of conservation of mass says when I start with something and I don't add any mass into the system and I don't take any mass out of the system, I just let it change form in the system, what I end with and what I start with have to be the same mass. What would it mean if it wasn't the same? What if I had 29 grams and when I'm done I had 30 grams? Well, either 1 gram was added to the system from the outside, or we just made something out of nothing. Which is probably the case? Which of those two options? Did we create something out of nothing? Who does that? God. God's the only one that creates something out of nothing. So when you have a formula like this and you say, yeah, I took the 30 grams and I produced 29 grams, or I took the 29 grams and I made 30 grams, you're playing God. That suggests you don't have that authority. You can't do that. However, God does give us the authority to take what he has made and rearrange it. And in my rearranging, it'd be like an artist that takes the canvas and has the paint, takes the mass of the canvas, takes the mass of the paint, takes all the paint and puts it on the canvas and makes this beautiful piece of work, but everything that you see was made out of something that existed before they started. And guess what? The mass of the canvas and the mass of all the paint on the canvas, if they used up all the paint, is going to be equal to the mass of the blank canvas and the mass of all the paint before the artist started. Because nothing new was made in terms of matter. A new creation of art was made, but it's just a rearrangement of matter that already existed. Okay? It says, talking about the elements, though, on page 50, I realize the bell's going to ring in just a moment, so we're just going to quickly gloss onto this. We'll pick it up here tomorrow. Talking about iron sulfide. And iron sulfide undergoes a change where it forms iron and sulfur. And every time 88 grams of iron sulfide is decomposed, it makes 56 grams of iron and 32 grams of sulfur. It always decomposes in the same relationship. We'll pick it up there tomorrow.